Welcome to the Explainer. Okay, let's dive into this. Today, we are completely demystifying the logic behind robotic hardware. When we picture robotics, we usually imagine these wildly complex, indecipherable algorithms and machines that almost seem to just think for themselves. But if we unpack the logic of software development, specifically looking through the lens of the Robotics XP7 curriculum, it actually reveals something so much more fundamental. To program a machine, you really just have to learn how to speak its hyperliteral language. So think about this for a second. What happens when a recipe is missing a step? Have you ever tried to bake something and the instructions just casually forgot to mention when to add the eggs? Or maybe they didn't tell you what temperature to set the oven to? Now, for us humans, a missing step is, well, it's annoying, but we usually just use context clues to figure it out. We look at the batter, guess the temperature, and kind of just make adjustments on the fly. But in the world of robotics, a single omitted step doesn't just mean a slightly dense cake. It leads to complete, total mechanical failure. See, the human brain is an absolute master of context. We naturally fill in the blanks using our intuition and our past experiences. Like if someone tells you to go out the door, they don't have to literally tell you to reach out your hand, grab the handle, turn it 30 degrees, pull it towards your body, and lift your foot. You just do it. A robot brain, however, possesses zero intuition. Literally none. It requires hyperliteral sequential instructions to function correctly. You can't just tell it to leave. You must meticulously program every single micro-movement. Section 1. The cake recipe rule. This is the big secret. Coding is effectively just writing a recipe. Miss a step, and the whole system halts. It really isn't some mystical language of ones and zeros floating in the ether. It's an exercise in hyperliteral architecture. You are creating a list of steps so exact, so perfectly sequential, that a machine with absolutely no common sense can execute the whole shebang flawlessly. Section 2. Meet the microcontroller. Now, what's really interesting about this slide is how we define this critical piece of hardware. The microcontroller is the physical brain we're trying to communicate with, and it operates entirely free of human intuition. It's a flawless thinker. It will do exactly what you tell it to do without fail every single time. But ironically, that is also its greatest weakness. It will blindly follow your commands step by step, even if your logic is completely and totally flawed. Section 3. The step-by-step square. Let's move to and see how this builds. So, imagine a small robot, right? Let's say a turtlebot, and you want it to draw a simple square. You can't just say, hey, draw a square. No way. You must mechanically map out the instructions. Step 1, move forward. Step 2, turn. Step 3, repeat. This rigid, incredibly simple 4-step process is the entire foundation of how that turtlebot navigates physical space. Forward, turn, forward, turn. By doing this, we are translating movement commands into exact robotic actions. We take this broad conceptual idea like a square, and we actively replace our human intuition with rigid, programmed logic. This is the very essence of software development for robotics. You have to break the physical world down into distinct mechanical steps. Because if your step-by-step logic map is flawed, the robot's physical movement will be flawed. Section 4. Program your teacher. Okay, to really drive this home, picture a classroom where the students are the coders, and the human instructor acts as the literal microcontroller. A student gives what they think is a totally normal instruction: draw a line. Now, to a regular human, you'd probably just take a pen and draw a line on a piece of paper sitting on the desk, right? But the teacher is acting like a machine. So, because the student wasn't specific, the teacher glitches. They might walk right past the desk, grab a permanent marker, and draw a huge line directly on the classroom wall, shouting, "Error! Glitch!" It's a hilarious visual for sure, but it perfectly simulates the harsh reality of coding. You have to assume absolutely nothing, or the robot brain will happily just draw all over the proverbial wall. And this brilliantly illustrates the sharp contrast between what humans think they just communicated versus what a literal machine actually processes. Clear communication provides exact, undeniable steps. Uncap the marker, place it in the center of the paper, move 6 inches to the right. But technical ambiguity, like just saying draw a line, leads instantly to errors. Treating a human like a literal computer exposes exactly where our natural language completely fails us in software development. Section 5. Avoiding the human glitch. So, the crucial point is this: technical ambiguity leads directly to errors. If there's a glitch in the system, honestly, it's almost never the microcontroller's fault. It is the human's fault for being ambiguous. Exactness is fundamentally required. But crucially, and I really want to emphasize this,
Coding is an exercise in creative thinking. Removing human ambiguity isn't just some boring technical chore, it's a massive creative puzzle. You have to creatively imagine every single possible way a machine might misunderstand your instructions and then design a foolproof recipe to prevent it.
We spend so much of our time trying to teach machines to understand us. But when we look at exercises like programming a turtlebot, does learning the rigid, precise language of robotics actually reveal our own human communication flaws? It really makes you wonder. Maybe in mastering how to talk to a microcontroller, we inadvertently discover exactly how much we take for granted when we just talk to each other. Something to chew on the next time you write a line of code. Thanks for joining us for this explainer.